Hi, this is for a video for compiler design, COMP442 and 6421. This is for week 6. Again, this week we're continuing and finishing the discussion on syntax-directed translation. The two topics for this week are going to be syntax-directed translation using a table-driven predictive parser, top-down, and the last lecture is going to be how you can generate an abstract syntax tree using syntax-directed translation. So let's go to the slides. So this is going to be quite a short video. Simple reason is that, as you're going to see, we saw much of this mechanism when we talked about how to do it using the recursive descent predictive parser. Many of the concepts are going to be the same, as you will see. So what's going to happen, what's happening here is that you have this common algorithm that is common or generic, dependently of what language you are processing using a top-down table-driven predictive parser. You're using always the same algorithm, right? Yeah. Pointer here. So you have this algorithm here. Of course, it's reading a stream of tokens, and then it is peeking into the table to actually, depending on what is the token and input, and depending what is the symbol it has on top of the stack, peeks into the table and basically starts parsing a certain right-hand side that the table is telling itself to take at this particular moment in time. Now here, there are some things that must be added to this mechanism that we saw before. Okay. So then here, as we saw before last week, what we're doing is that we're introducing the notion of semantic attributes. So you're gathering information as you're doing the parse, and you want to somehow connect these bits of information that you get when you reach the leaves of the tree. You get information and then it starts migrating up in your parse tree, and you want to connect these informations together, aggregate this information together to get coherent pieces of information that you aggregate together that eventually will tell you the complete information that is necessary, that is explaining the meaning of a whole syntactical construct, for example, such as a variable declaration. Okay. So you're gathering information at the leaves of the tree, it gets up, you aggregate it, and then you get more complete information about a whole concept. So that's what's essentially happening. So as we saw last week, you start having semantic attributes, which are gathered and processed by semantic actions that you are introducing in your parsing process. So what's going to happen with the top-down table-driven predictive parser is that you're going to insert some new symbols inside of your right-hand sides. Because when you actually get you peek into the table, it's basically telling you what right-hand side to use, which is a sequence of symbols, which are used to be terminal and non-terminal symbols. Now we're going to introduce other symbols, semantic action symbols, that are going to represent the fact that you want to trigger the execution of a semantic routine that represents a semantic action. So by introducing these semantic actions inside of your right-hand sides, so theoretically speaking, what's happening here is that your grammar becomes what is called an attribute grammar. Now, I've already said last week that we're not going to cover attribute grammars here in theory, but that's what we're using. But even though I chose in this course to not describe the theory related to attribute, the processing or representation, mathematical representation of attribute grammars. So what's going to happen is that you're going to insert inside of your right-hand sides some new symbols, semantic action symbols, and then you're going to introduce them inside of your right-hand side so that when you're going to fetch the right-hand side from the table and you're going to push it on the stack, then suddenly you're going to have new kinds of symbols that are going to be pushed on the stack, the semantic action symbols. So what's going to happen then is if you are retrieving the next symbol from the stack as you're parsing, then what's going to happen is it's going to trigger the execution of the semantic action that's associated with this semantic action symbol. Okay. Another problem is that you have somehow to store these semantic records. Now, as we saw last week, you can actually use, like I've shown you how you can actually use a stack to store the semantic actions, particularly when you use the recursive descent predictive parser. You can have an explicit stack to store your semantic records. Now you might say, well, we already have a stack in the top-down table-driven predictive parser, so I'm going to use the parsing stack. It's not so easy because as we will see, the parsing stack and the order and the frequency in which these are generated, the symbols are generated and the semantic records are generated, it's not necessarily synchronous. So you actually need to have a additional stack, which is the semantic stack. So you need to design another stack that are going to contain only semantic records. Okay. So here we go, and describing here, this is our good old grammar for the expressions. What we did here is basically introduce new symbols that are in red here. And what these symbols are doing, they're essentially doing the same operations, exactly the same operations as we saw when I described before the attribute migration, when I described, for example, the recursive descent predictive parser operation for the syntax-directed translation. So eventually, as we saw, then the information is gotten from the leaves of the tree. And then the information starts from the leaves and then migrates to certain nodes in the parse tree. Okay. So this ID here, you get the information about the ID from the token that you've just parsed. And then that becomes actually a semantic record that is being produced by the f function. Then, so that's one semantic action that takes the information from the token, puts it into a semantic record, and then that becomes this synthesized attribute of your f. Then, as we saw earlier also, this t prime here needs to actually inherit this synthesized attribute of the f, and that becomes an inherited attribute from the perspective of t prime. That's an inherited attribute. So then you need to have another semantic action as to do this sideways migration from the f to the t prime. Then you need another action that will take this fs here that was produced here, which would have been stored on the stack, take this fs from the stack and then transform it into a ti and then push a ti back on the stack. Thus, the t prime will be able to fetch the t prime I from the stack. Okay. So you see that all these attribute migration steps are all exactly the same as what I explained before last week. Okay. Except that here, what you're doing is that you are essentially putting them explicitly as processing steps inside of your right-hand sides. For example, the rule A here, semantic action A here. So for example, the rule E, you have TE prime, but now you have TA E prime B. So what is the rule A doing? This rule A here, so you're processing this E at this point. So E is T E prime. So as part of the processing of this parsing of the T and then parsing of the TE prime, eventually what you want to do, as we saw last week, what you want to do is that the attribute that's going to be processed by the T is going to be given sideways to the E prime. So this TS that this one would have produced, which is assumed that's already on the stack, is going to be fetched from the stack as a TS, and then it's going to be pushed back on the stack as an E prime I, so that the E prime here can actually get the E prime I. So that when you will process the E prime here, that the rule C here, as you see, the C rule will actually get the E prime I from the stack. Okay. So this is the same kind of very precise orchestration that we were talking about last week. It's just that it's using a different mechanism. It's using here the top-down predictive parsing method, but that is using a stack and a table. So, so let's go into the other rules here. So E prime gives plus TE prime. That becomes E prime is plus TC E prime D. So let's say you go to an E prime here in the example. So the E prime here, what first this must do is to actually get this information that it got here from the T. And as we just saw, then the E prime would get the E prime I that is provided to it by the T through the stack. And then this E prime here is going to get so what this TS here is of course the left argument of the plus operation it is to process. And then the right argument of the plus is actually what it gets by way of this here. So that would be the synthesized attribute of this E prime here. So this E prime rule here in this case must provide this E prime S to this E prime rule, so that now it has the left and the right operand of the plus, and then it can actually process this this operation. So that's actually what is done by this semantic action here. And then, of course, after this has been finished, then the E prime I has been produced, which is then passed by the other E prime, which would return it as using the rule E, which is transforming the E prime I into an E prime S. Okay. And then eventually this D rule here, which send up this E prime S to the rule that has called the E prime I, the rule E prime in the first place, which is this one here. And then eventually this B rule here would take this E prime S and then somehow promote it up on the tree into an ES, thus returning the entire tree. I'm not going to do all the processing steps here. So you get that it's exactly the same process as I described last week. It's essentially doing the attribute, gathering the attributes at the leaves of the tree, and then making the semantic attributes propagate up in the tree by aggregation and verification. And eventually, as we will see, what we will do with that in the project is to build an abstract syntax tree by creating nodes at the leaves of the tree. And then as nodes are as the parsing process is getting to a higher level node, then you will actually take the abstract syntax tree nodes, you will graph them together to create a subtree for this syntactical construct that you're currently parsing. So you see that's, again, exactly what we described last week. That's here just a second example. Then here we see that this is the parsing trace of parsing E ID times ID plus ID. So I'm not going to go into all the steps here, but again, just maybe if we can do a few steps. So of course you push on the stack the end of the program symbol, then you push the starting symbol on top of the stack, then you go EID, you go in the table. That's basically telling you that you should apply rule number 1. Rule number 1 is, in this case, and that's where it becomes interesting, what is rule number 1? Rule number 1 is this one here. So you see that I have added these symbols inside of my right-hand sides. So I will actually push onto the stack B E prime A T. So I replace E by B E prime A T, okay, where B and A are, of course, symbols representing semantic actions. So as everything is the same until, for example, like here, when I get on top of the stack here, I see that there is a semantic action symbol. So you need to add this case inside of your parsing algorithm so that you have now a third case in the loop, so that if what you see on the top of the stack is a semantic action, then you would actually trigger the execution of a semantic procedure, a procedure that implements this semantic action. Now, what is K doing? So what is the rule K doing? The rule K is actually here after for the definition of F. The rule K is essentially that you call the make node function that's going to create a node for this identifier. Okay. And then it's going to actually say that this node is a synthetized attribute of F, or an FS. So it's essentially pushing that onto the stack. So if you see my rules here, they're all something equals something. So what is to the right is things that you pop from the stack. So for example, here, or some function that you call that is going to itself possibly pop things from the stack. So in this case here, it's a function that I called that is creating something which I then push onto the stack. Okay, and the name here tells me what kind of symbol it is that I'm pushing onto the stack. In this case, I'm pushing this node onto the stack as a semantic record, and this is now a synthesized attribute of an F. Okay, so that if some other function is, some other semantic action is retrieving something from the stack, it would, for example, be expecting an FS on top of the stack. Now, you don't necessarily have to identify them, the semantic records that you push and pop on the stack. You don't necessarily have to identify them as being FS or TI or whatever it is, but it is actually very useful if things are going wrong, that you can see what kind of nodes they are, okay? What kind of semantic records they are. Because you see that many of the rules, what they do, for example, this one is taking an FS from the stack, it's popping an FS from the stack, and then it's pushing it right back as a T prime I. Okay, so there's no processing that was done except from the fact that this FS becomes a T prime I, and it's exactly the same semantic information. Okay, except that now it was an FS that, it used to be an FS that was on top of the stack, and now after this operation, it is now a TI. It's still the same information that is on top of the stack, but the kind of node that it represents, or semantic record that it represents, has been changed. So you see that all of these here that don't really do any addition or aggregation of information, all they do is just rename the records to another kind. Okay. But again, you don't have to do them, these transformations, but I would strongly advise that you do, because if your stack gets corrupted, goes out of sync, then at least when you look at your stack and you see that there's a TS and FS and so on top of your stack, then you can observe more accurately what's the problem that is happening. So, okay, so this here, so at this point here, I got my K rule. The K rule says take a token, and then actually this token that I have had identified here, and then put this the information that you extract from the token, which is the ID name, and then put it into the semantic record, and then push it onto the semantic stack. So that's where here you see that I am actually pushing some information on the semantic record onto the stack. So here, this is my information, my semantic information. This is the value of ID1, and it is an FS semantic record. Okay. And then, of course, I pop this symbol from the stack. Then the next thing, I'm going to apply rule F. Now, what is rule F saying? The rule F is used here. So essentially, this rule F here is the rule that is called after this F has been called, which we just did, and is going to somehow process the inherited, transform this synthesized attribute of the F into an inherited attribute of the T prime, basically processing or sending this semantic record sideways across the tree. So that would be what you're doing here. Okay. So the F is being traversed across the tree so that it can now be available to the T prime here for processing. And then after this F rule, what it does is get the FS from the top of the stack. This F rule takes an FS from the top of the stack and transform it into a T prime I. That's what we see here. It takes the FS from the stack, pops it from the stack, renames it into a TI, and then pushes it back on the stack. So you see that it's very handy that you can actually know what is the kind of attribute that is. It's still always, you see here, that's always the same information that you have on top of the stack. But then it's handy to have what kind of semantic record it is, so that if you want to be able to trace what's actually happening if something goes wrong. So not going to go into all the steps here, but one thing you might see finally is that you see that the semantic actions that are applied are K, F, K, H, J, I, G, A. So that would be exactly the same order. Which one is it? Times. So you see that the information, the way it flows, is using the rule number K, the rule K, then the rule F, and then the rule K, H, J, I, G, A, so on and so forth. So if you trace the tree, if you do a traversal of the tree, then every time there's a attribute that is being migrated using these rules that I have noted here, then they are eventually called in that particular order in the parsing trace. Okay, so that's if you want to figure out what are the semantic actions that you need to have, and in what order and where in the tree should they be added. And it's very handy to be able to draw a tree like this for every kind of syntactical construct you will be constructing, and then figure out where this information needs to be put, which then tells you where you would introduce these semantic actions inside of your right-hand sides. Okay, so that's generally the procedure that you will have to follow for every of the different syntactical constructs that you will have to process. And then eventually you come at the end, and then at the top of your tree, you have the entire semantic record for the entire program. Eventually, as we will build the abstract syntax tree, then At the leaves of the tree, you will gather information about the nodes of your abstract syntax tree. Then you'll aggregate these nodes to form subtrees, and they will aggregate until you come at the end of the processing of the whole program, and you will have on top, as a result of the return of the parse, it will actually return the node that is on top of the abstract syntax tree for your entire program. That's how it's going to go. So again, you see that here it seems simple, but of course that assumes that you've already listened to the video when I describe what is a semantic action, semantic records, the attribute migration, and so on. So if you're just jumping on this video here and think that you're going to understand everything, then probably you should realize you should listen to the videos from the week before if you want to have the whole understanding of the whole thing. So that's it for this video. Thank you.